The first IBM PC, or personal computer, that's what the PC stands for, was introduced in August of 1981. In 1981, it sold for $1,600 and it had 16K of RAM. That's K, not G, but 16K of RAM. And it it didn't even come with a hard drive. How could you possibly go from that PC to what we're using today? What I'm going to do is talk about why some of the same things that were developed, the same chip, the 8086 that was developed then, is still part of the basis of every PC that we have today. Intel was trying to get away from that architecture, but AMD produced some very valuable chips recently that competed and still had the old architecture of the IBM PC. But we're going to talk about how much different things are with the PCs today. And we're going to get down right into the nitty gritty details. So if you don't like the details, this video is not for you. I'm going to go down into the guts of the code, of the BIOS, of the ways that the hard drive is first loaded in there into the operating system, and use Linux as the operating system. Now, why am I using Linux? Well, it's pretty easy for me to answer that question because Linux is open source, meaning I can show you all the code that's in Linux and all the code that's in this BIOS by using a product called Coreboot. Coreboot is an open source BIOS, or we'll talk about later how it's really a piece of the pie of BIOS, and there's a payload involved. The payload is also going to be an open source product called the Grand Unified Bootloader, or GRUB. So if you're ready, I'm going to transition away from this onto the screen, share some screens, and we'll talk about the nitty gritty details. Here's my editor, which is Notepad++. It's good because it makes different colors of the characters and it makes it easier to see what's going on. Let me see, and let's look at the files that I'm going to go over. One is reset. That's when you first instruction that is executed, the reset. Then entry 16. Now notice it says 16. That's because the code and the processor looks like an 8086 at that time. It's only a 16-bit processor, a 20-bit address, and a 16-bit data bus. That's some of those pins are shared with the address bus. Pin count was really important then. Then there's entry 32. That's where we start setting up I should say that this sets up the thing called a global descriptor table so that when we go to protected mode, it knows what a code segment is and stuff like that. Then in here in entry 32, we will add create the data segments that are needed. Even though we're not going to use the traditional RAM right away, we'll find out whether we're in SPI-ROM, and then we'll find out what's going on there. And then from 32, we go to this file named cache as RAM. Cache is considered the internal, let's say it's very closely tied to the CPU on a system on chip, which is the way things are set up now. Rather than just a CPU communicating to external devices, you have a system on a chip that has a CPU core in there, and then it has cache memory, which makes things happen really fast. We'll talk about that a little bit. And then anyway, that's to set this up so that we can use that cache, which normally is just for temporary storage. We're going to use that cache so that we can just use it as RAM, so we don't have to use the external RAM. Because when we first start up in Coreboot, what happens if the RAM chips are screwed up? Well, the thing won't run. So we're just going to use the cache as our RAM, which is going to really speed things up a lot rather than reading from the boot ROM, which the access is very slow. We can talk about that more specifically. And here's the boot block. The boot block shows us what the memory allocations are for these different things. So that'll help us see what memory addresses the spy ROM is mapped to. This ID section is really not an executable. It just shows us where the core boot version and all those little particulars go, and they're very close to the reset block. And then finally, it gets really complicated. I don't know if we'll get to it on this video, but the cache as RAM stuff is very complicated, and we use vendor code from AMD to do this. By the way, the AMD 64-bit processor that we're talking about is something that would fit on AMD's motherboard called a Bilby, and with the SOC is considered a Stony Ridge. These items are necessary so I can pick and choose and build our imaginary computer out of what we're talking about. Finally, copy data section is a pretty simple thing. This is where we put the data into the new stack and cache as RAM so that we can then call C code and then start into doing a more traditional programming environment with the cache as the data, and we'll still execute boot block out of the ROM for a while until we can do transfers of what's called a core boot file system file into there. So that's a lot of stuff. I told you that would be nitty-gritty details. So let's begin. I'm going to look at boot block first and see what we got there. Let me go down to the very bottom, because when you do a reset instruction in the processor, it goes to this address. Now I've got a lot of F's here, and the F's stand for hex code 15, which is all ones, and the 0 at the very end. This ends up being a 32-bit address, which is what even though we start in 16-bit mode, the processor looks at this as a 32-bit address. Notice it's labeled as x86 reset vector. The address at this point is this reset vector. Here's the little identifier for reset vector. And then here's what's called a section called reset. The reset section has the reset module code, which we'll look at in reset 16. I'm sorry, in reset 16.s, and then we will go on to some other little items here. I mentioned the ID section. The ID section is, let me go up here to it. Here's the ID section up here. This init. Oh, no, let's go up. Well, let's see, where are we? I'll try to get this. Okay, here's the ID section. The ID section that's labeled as ID, amazingly. And this ID section is at very high memory addresses in this ROM chip. And that's where the information about the version, the core boot, various things about that so you can look that up and find out what kind of software is in there by using software instructions. Let's see, after the reset instruction and so on, we have to fill that information, byte 0 down to a very high address, FFFFFFFC, and that C stands for the hex equivalent of 12. So we're very close to the very end of this flash ROM. The header pointer goes there. That's a 32-bit value, so it takes 4 bytes. That'd be C, D, E, F. And there's the very end of the boot block. So Let me review that real quickly here. Here's the reset vector. That'll be the first area of memory that's executed, and it will jump to the entry 16.s. So once we go to that level, let me see where I'm going next. This is, talk about the ID section. The ID section is not executed, like I said. And these things, ECFW pointer, let's see, there should be a fit pointer in there. Okay, there's a fit pointer, there's an ECFW pointer. These things are defined as if you have an Intel processor, which we don't have an Intel processor, it's an AMD, so those things will just be 0 bytes long. So what that means is that the ID section is really bumped right up against the x86 reset vector. That's so we don't have any lost bytes in ROM. We're being very efficient about taking care of that. So let's see. Another thing to talk about is that really what we're covering is the early assembly code size, which is all bumped up very close to this ID section. And that is we'll find out that we'll jump to farther, well, to lower addresses so we can execute without having to keep jumping over ourselves, leapfrogging into lower and lower addresses. So really it goes something like this. You jump to the 16-bit code, and then the 16-bit code jumps to the 32-bit code. That's when we go into protected mode. The 32-bit code, and then that goes into the, let's see, cache's RAM. So really, entry code will be at the lower address. Entry 32 will be at the next highest address. Cache's RAM will be at the lower address from that. And then we'll jump all the way to a lower address, which is really the lowest address of the boot block code. Pretty wild. It's probably have to slow the video down and listen to some of this stuff. But I've been thinking about it quite a while, and this is how all these things fit together. Now, let me see where we stand next. Okay, let's go to the reset vector code. This is a little bit strange, and I want to point out some things about it. Here's reset. Well, where's the executable code? Where's the assembly instruction? Well, they had some problems compiling and building with the traditional jump relative 16 to this is the start 16-bit code, the start of this entry 16.s code. And so they had to do some manipulation arithmetically so that it will act like a 32-bit in some ways, but act like a 16-bit in the other ways. The address stored here is a 32-bit value, which should mess up the jump relative instruction because it's supposed to be a 16-bit, and this stored here is a 32-bit, so it's hard-coded like this. And because, here's a little funny thing, this works because the x86 is little endian. That means the lowest address, the lowest value byte is at the lowest address rather than big endian, which is more like you'd write the thing down on paper. Not going to go through all that detail, but anyway, that's what this is all about. So we should be able to move into the start 16-bit code next. Okay, let's go to the very beginning here. Now we got some instructions. Now, if you're used to assembly code, that's will be a little bit easier for you. Here it shows something that I thought was very interesting. Core Boot was developed by employees of a government, U.S. government contractor outfit. I don't know if the U.S. I think the U.S. government didn't actually pay for Core Boot, but the employees of Core Boot, let's see. Okay, there's the university. Which university? Okay, here we go. This software has been authored by an employee or employees of the University of California. Okay. They are the operator of the Los Alamos National Laboratory under contract, blah, 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 U.S. Department of Energy. So that is kind of different. Core Boot, these people must be pretty good at their job, which is why they came up with a lot of these ideas. But it is free software. I downloaded it for free, and I can even modify the source code, which would probably break everything. But this is just so we can understand what's going on. Okay, now assembly code. You might not be used to assembly code, so I'll kind of go through this slowly so that we don't get too mixed up. First thing is, remember we are in what's called real mode, which, I don't know why it's called real. It should be called 16-bit mode. The 16-bit mode is what the 8086 ran in. So this still kind of looks like 8086 at the very beginning. And if we go down here, let's see, start bit. Here's the start bit, and here is first thing we do, clear interrupt. Clear interrupt. What are we clearing the interrupt for? That's so there's no interrupt vector table set up yet. So if we have an interrupt, which does just exactly that, if you have an interrupt, hardware or software, it changes the program execution and goes off to an address on the interrupt vector table. Well, since we haven't set any of that stuff up, we have to clear the interrupt. Now what we do is save the BIST. BIST is the built-in self-test. The processor has a way of indicating whether it's running correctly or not. So obviously, if it doesn't work correctly, then that's not going to work. That's not going to have us give any good results. Then what we do is we move that result to another register, the base pointer, just as a temporary holding point. And then it says post code. This post code function can be found in a header file called, strangely enough, post.h, and there's a postcodes.h, which has the values of these symbols here. And those symbols will indicate a message to a debugger where you're actually watching output ports and you can read stuff directly. So we're communicating to some kind of debugger environment. So somebody that's running Core Boot and maybe it's broken or something, you want to figure out what's going wrong, you can watch these post codes or output bytes put on the output ports and kind of get an idea what's going on. This next thing, which I have looked at a little bit, is first of all, when you exclusive OR EAX and EAX registers, that zeroes them out. If you know about exclusive OR, you'll know how that all works out. If you don't know exclusive OR logic, then you've got a little bit more study to do. This move instruction does exactly that. It puts 0 in this control register 3, which has this translation look-aside buffer. What in the heck is that? I don't know. I'll do some more research on that, but it wants to invalidate that and that solved a particular problem that the code had. Here's a bunch of talking. Okay. Now we're getting down to brass tacks. Here's the code segment selector, which actually includes the upper 4 bits of the 16-bit, 4 bits of the 20-bit address block, which is only accessible up to 1 MB. That's why we had to put those all these assembly files at a higher address, which was closer to the reset vector, because we only have a 1 MB space to work with in 16-bit mode. Then let's see, here's a IDT, that's interrupt descriptor table, and GDT, which is global descriptor table. This says a null IDT, which means that there is no interrupt descriptor table yet. All we're doing is setting up code segments and data segments, and we'll see that in a little bit. Finally, we subtract, let's see here, what am I doing? Okay. We had to put that descriptor table, and then we load the interrupt descriptor table. We have to have something in its place, even though it's kind of going to be a null value. And we use the, we've got to have all the information. So we have a BX register and the code segment selector. That gives us the address for the interrupt descriptor table, which is null. I don't know, maybe we'll go through this and make more sense of it. Now, finally, we've got the global descriptor table, which is a series of information. Once we look at the details, it'll make more sense to you. There's a file missing up here, GDT init, but we'll have to get that pretty soon here. Probably have to break this video up until we can get that done. And let's see, we include master system registers, and it says include only if you're an Intel processor. So just kind of wipe that out in your mind. That really doesn't exist on this AMD example. Now we have here's the control register 1. This will set the protected mode byte. Now notice that we AND this value with the EAX register. Now let's see, what is in the EAX register? Let's see. Oh, wait, ahead of myself. Let's see, what's in the AX register? Oh, that's a copy of the code segment register. So I come down here. I told you it would be nitty-gritty. We're acting just like the processor, or you'd say, what I like to do is think of it as Bitman, the person that's actually in the arena performing the instructions. Now we move control register 0 to the EAX register, and we put and this value with that, or it with this one. This one sets the zeros. When you do an AND instruction, that sets the zeros, and this one sets the ones because you're doing an OR instruction. So we copied the control register 0 into the EAX, then we put these values, or we change the values of this control register here, using this one to set the zeros, this one to set the ones, and then finally we move that EAX back to CR0. At this point, let's see if I can show you the protected mode byte. Here's the protected mode byte is 1. We restore that value of the built-in self-test, and it says now that we are in protected mode, jump to a 32-bit code segment. And let's see where we are here. Okay, the global descriptor table is defined in global descriptor table init or GDT init.s. It has a 4 gigabyte code segment at 08 and a 4 gigabyte data segment at offset 10. Remember these when I stop and get that GDT init file. And let's see, once here's the long load jump. Once we do this, this will jump from 16 to entry 32.s, which is actually loaded right below it. So we're really not jumping a very far distance, but we're doing this mainly to load the code segment and this address called boot block protected mode entry. Here's a file that I didn't have ready when we were talking just previously. It's called gdt init.s. And this is global descriptor table, and it initializes it. But all we need to do, it's got some other stuff in here where you can call this from another function. We're not ready to call anything right now, but that would load the global descriptor pointer from the GDT pointer. So this is the address that points to the global descriptor table. Now, if we move down here through all this stuff and kind of ignore that, we get to the GDT, which the GDT pointer will point to this section of memory. So this is just describing the memory. Now, the way that that's set up is the first descriptor table is just a dummy, or it's never used. So that one's all just emptied out. So it says select GDT 0 unused. Now, if we select GDT 08, then we have all of these bits. Now, decoding these bits is a little tough, but basically what it does is these zeros, and these zeros show us the base address, which now we're going from a base, addresses that are all Fs are at the very end of the 4 gigabyte range to the very beginning of the 4 gigabyte range. Now, that poses the question, what in the heck are we doing way at these low addresses when we're all the way at the upper edge of that 4 gigabyte boundary? Our BIOS ROM, or this SPI ROM, is certainly not as big as 4 gigabytes. In fact, it's only about 8 megabytes typically. So somehow we've got to have a big displacement. Well, the limit of the displacement, if we take all these bits and decode them, we get a limit of 4 gigabytes. So it doesn't matter that we're at the address 00000, because we can have an offset from that, or displacement into the segment that is all the way up to 4 gigabytes. So we can easily create addresses that'll go into the SPI ROM, which is what we need. Now, this is the code segment. And if you look at these two sets of numbers, you might have to stop the video to look at the sets of numbers, but the only difference between them is a 9B and a 9.3. And the difference between these is the 9B versus the 9.3 is the difference between defining a code segment and a data segment. Now, notice there's also select another code segment. Well, you can't have two code segments. You've only got one code segment, but notice it says 64 bits. 64 bits. Well, we're not in 64-bit mode, we're only in 32-bit mode. So we'll come back to this, but this is still in there. So notice this thing is kind of a big block of memory that describes what's going on. So we can add even more than just these four to that descriptor table if we wanted to, but this is all we're going to have right now. Offset 0, which we won't use, offset 08, offset 10, and offset 18. Now, where are we now? Let's see. We load the global descriptor table? Let's go back to entry 16S and see if we loaded the global descriptor table. Let's see, restore BIOS, long jump. Long jump. Oh, ROM code segment. Notice it says this ROM code segment, if we were to look this up, this would be 08, which would point to the code segment, and then this will be the offset, which can be a 32-bit offset into this label called boot block protected mode entry, which we'll find is the starting point of entry 32. So we didn't actually load it. It was already loaded for us, or we already referred to it in GDT init.s. Now, hopefully you're not too confused. Oh, backing up a little bit, there's one thing I wanted to point out is when we did that postcode, here's the postcode code. Look how small it is. We move the value, we move the value that's in here, and I'll show you the area where we get the value. We move the value to the AL register. That's just the lower 8 bits of the A register, and we do an out bus, which just goes to an IO port. And so we take that code and put it to the IO port. Every time it does a postcode, it goes to this output port, which if we have some debug tools, we can watch that and see what the code is. Now, one last thing, where are the codes? Here's all the codes. And let's see if we see some of the codes that we were talking about. Postcode ROM stage main. Where's the postcode that we had early? There must be another postcodes. Let's see. If not defined. Okay, I kind of screwed up here because I don't see the code that I wanted to show up. So if I look a little bit further, maybe I'll fill that in at a later time. But there's probably another postcodes that I should have referred to the first time. Let's see if that's in our entry 16S. Let's see which postcodes we wanted to look up. It should be an include file to bring that in. Let's see. Include postcode. That's all it was. How do we know what the value of that postcode is? Let's go back to postcode. Okay, somehow entry 16 has got to come up with this value, postcode reset vector correct. So like I said, I'll go back and look that guy up later. Now let's go on to entry 32 and see what's in there. This is a short one, so this might be a good place to end up. Let's go in here. Here's boot block protected mode entry. Here we're saving that value again onto this built-in self-test onto the EBP register. Postcode, here's another thing, enter protected mode, and we're moving the ROM data segment, which is 08, and that's the code segment, onto AX. Oh, I'm sorry, that's the data segment, which is hexadecimal 10 for the data segment, and we're setting the data segment or data segment selector to 10 for the data segment, the extra segment, the stack segment. The stack segment's really important for us. And then we do exclusive OR the A register, which zeroes it out. So we zero out these two other segment registers, which are not being used right now. So we just kind of zeroed those out. I guess that would be the null segment. Maybe that's why we need the null, because we don't have that. Okay, we restored the built-in self-test value. Here's the thing: if you have a debug tool, which is the JTAG debug tool, those are kind of complicated to explain. They get into the internals of the IC, so let's not talk about that. And then let's see, move the control register 4 to the EAX register. We OR it with some value here. Value OR CR4OS. Let's see what that does. Oh, if config SSE. So we're not doing that. So look at, there's nothing in this file. We scratch out all the stuff that really doesn't apply to our situation. All we have is it loads the data segments and nulls out some of these selector segments that were not going to be used. And we don't do the config. That config is not done, so we skip that. Then we just jump to boot block pre-C entry. And boot block pre-C entry is, go up to this file called cache as ram.s. And here's the boot block pre-C entry address that we go to. And now we do a postcode boot block CAR, which is setting up cache as RAM. Now, cache as RAM is going to be extremely complicated, so I'm going to hold off to the next video. A whole video could easily be dedicated to the cache as RAM process, and I haven't walked myself through all of that, so I can't walk through all that now. So hopefully that's kind of gets you on track with how this is going, and it gives you an idea whether you want to keep watching this kind of stuff, because it is weird stuff. How was that? You're going to keep watching these things? These will keep going for a long time. So hang with me if you can. I hope so. I hope my friend in Australia watches these, and I'd like to get his feedback on this kind of stuff, because it's so much different than the physics type information that I talked about before.